morning, everyone. Thank you for joining us today for another deep dive into the fascinating world of technology.
Hello, everyone. Thank you for having me. It's a great pleasure to be here to discuss this important topic.
Great to have you. So last time we really got into the CPU, the brain of the system.
hmm
But a super fast brain isn't much good if it can't get the information it needs quickly, right? It needs its fuel.
Exactly. That's
Yeah.
the crux of it. The CPU might be lightning fast, but overall system performance, what you actually feel, depends massively on how quickly that CPU can access data.
And that access speed is where things get complicated, I gather.
They do, because there's this fundamental engineering challenge. You basically can't build one type of memory that's super fast, has massive capacity, and is cheap.
Ah, the classic trade-off. Pick two, maybe.
Pretty much. Or rather, you find different balances. And that's why computer architects came up with this elegant solution, the memory hierarchy.
Okay, the hierarchy. Sounds like a pyramid structure.
Yeah. That's a perfect way to visualize it. It's a tiered pyramid of different memory and storage types. Each level offers a different balance of speed, size, and cost.
All designed to keep that hungry CPU fed as efficiently as possible.
Precisely.
So that's our mission today then. We're going to unpack this memory pyramid, look at the trade-offs, talk about volatile versus non-volatile memory.
Compare the interfaces like SATA and NVMe.
Right, and demystify that clever OS trick, virtual memory. This is definitely for you if you're a tech enthusiast or student wanting to understand what's really going on under the hood.
Absolutely.
Okay, so let's kick things off with that core problem. What is the fundamental engineering trade-off that necessitates this memory hierarchy?
Well, as I hinted, it really boils down to those three key things. Speed, meaning access time, capacity or size, and cost per byte.
Okay.
It's currently just not possible, physically or economically, to make a single memory tech that aces all three.
Extremely fast memory, like nanosecond access. It's incredibly expensive per bit and not very dense.
I mean, you can't fit much of it in a small space. Exactly. On the other end, you have technology that lets you store terabytes very cheaply, but accessing a specific piece of data can take milliseconds, which is an eternity for a modern CPU.
Thousands, millions of times slower.
Right. So architects use this tiered structure. The guiding principle is keep the data the CPU needs right now or very frequently in the smallest, fastest, most expensive layers closest to it.
And the less frequently needed stuff gets pushed further away.
Exactly. Down to the larger, slower, and cheaper layers. It's all about probability and access patterns.
That makes sense. I know there's a really common analogy used here, the scholar's desk. Could you walk us through that? It seems quite helpful.
Oh, yeah, it's a great one. So imagine a scholar working intensely.
Okay.
The single thought or fact they're literally writing down right now, it's like CPU registers.
Yeah.
Level 0. We're talking maybe less than a kilobyte total, access in under a nanosecond, instantaneous, but incredibly limited capacity, highest cost per bit.
Just what's in their immediate focus.
Exactly. Now, the open books and notes spread across their desk, the things they're constantly referring back to. That's the CPU cache, L1, L2, sometimes L3.
Still very close, very fast.
Very fast, yeah. Maybe 1 to 20 nanoseconds access. Capacity is larger, kilobytes to megabytes, but still very expensive and limited compared to main memory. That's your level 1, and it's volatile, needs power.
Okay, so desk space is limited, but quick to grab things from. What's next?
The book's on the bookshelf. In the scholar's office, they have to physically get up, turn around, find the book, open it. Takes a moment.
Right.
That's your main memory, your RAM.
Uh,
Level 2, now we're talking gigabytes. Access times are maybe 50 to 100 nanoseconds. Still fast compared to storage, but definitely slower than cache. Still volatile, too.
got it. Bigger capacity, takes longer to access.
And then the vast collection of books way down to the university library's archive. Huge capacity, right? Terabytes, potentially.
That it takes a real effort to go get something.
Exactly. That's your persistent storage SSDs or HDDs. Level 3. Access times jump dramatically. Microseconds for SSDs, milliseconds for HDDs. Much, much slower. But the cost per gigabyte plummets. And crucially, it's non-volatile. Data stays when the power is off.
And you could even add another layer, right? Like deep archive.
You could, yeah. Level 4. Offline or archival storage. Think tape backups or cloud archival tiers. Petabytes of storage, potentially, but access could take seconds, minutes, even hours. Lowest cost, definitely non-volatile.
So the whole analogy illustrates how keeping the most relevant info close by makes the scholar or the CPU work efficiently, constantly shuffling things.
Precisely. It's a continuous dance of data moving up and down that pyramid based on usage patterns.
Fantastic analogy. Okay, let's zoom in on the top part of that pyramid for a bit. You mentioned volatile memory. What are the main types there, and how do their physical structures differ?
Right. Volatile memory, the computer's short-term workspace, gone when the power goes. The two big players are SRAM, static RAM, and DRAM, dynamic RAM.
Static and dynamic, what's the difference?
Static means SRAM holds its data as long as it has power without needing to be refreshed. Internally, each bit is stored using a flip-flop circuit, typically made of 6 transistors. It's complex.
Okay, 6 transistors per bit. That sounds dense in terms of complexity, not storage.
Exactly. That complexity makes it very fast and stable, but also uses more power, generates more heat, is less dense storage-wise, and is significantly more expensive to manufacture.
And DRAM.
Dynamic means the memory cell itself is simpler, just one transistor and one tiny capacitor per bit. The capacitor stores the bit as an electrical charge.
Ah, but capacitors leak charge, don't they?
They do. That's the dynamic part.
Yeah.
The charge leaks away quickly, so the memory controller has to constantly read and rewrite the data thousands of times per second just to refresh it and keep it alive.
So, simpler structure, higher density, cheaper, but needs that constant upkeep and is inherently slower because of it.
You've got it. That's the fundamental difference in structure, leading to different characteristics.
So, given those characteristics, where do we actually find SRAM and DRAM being used in a modern computer?
Well, given SRAM's incredible speed, but also its high cost, higher power draw, and lower density, it's pretty much exclusively used for the CPU's cache memory.
L1, L2, L3, right next to CPU cores.
Exactly. Its speed is absolutely vital there to act as that buffer between the super-fast CPU and the relatively slower main memory. It keeps frequently used instructions and data right there.
Makes sense. So DRAM takes on the role of main memory.
Precisely. DRAM is slower than SRAM, yes, but it's much, much cheaper per bit and significantly denser. This lets us have large amounts of it, the 8, 16, 32 gigabytes or more of RAM we see in typical PCs at a reasonable cost. It's the main workspace for your operating system and all your running applications.
The workhorse memory. Now, you mentioned RAM. How has DRAM technology itself evolved? I mean, CPUs keep getting faster, especially with multiple cores now. How does RAM keep up?
It's had to evolve significantly. The RAM we use today isn't just plain DRAM, it's typically SRAM, synchronous DRAM.
Synchronous.
Meaning it synchronizes its operation with the CPU's system clock, or memory bus clock. This allows for much more predictable timing and higher transfer rates compared to older asynchronous DR.
Okay, that was the first step.
Then came DDR double data rate SDRAM. This was a huge leap. It transfers data twice per clock cycle, effectively doubling the peak bandwidth.
Ah, DDR. I think most people have heard of that. DDR3, DDR4.
Exactly. We've seen successive generations, DDR, DDR2, DDR3, DDR4, and the current standard is DDR5.
And each generation is faster.
Yes, each new generation primarily offers higher bandwidth, more data transferred per second, and often lower power consumption too. DDR5 in particular represents a really significant jump in both speed and potential module capacity.
Which is crucial for feeding those multi-core CPUs we mentioned.
Absolutely critical. Modern CPUs with many cores can process data in parallel like never before, so they are incredibly hungry for memory bandwidth. DDR5 helps satisfy that hunger.
Okay, fascinating evolution there. Let's shift gears now to the other side of the hierarchy. Non-volatile memory, the stuff that sticks around. What about ROM? Where does that fit in?
ROM, read-only memory, is sort of the bedrock. As the name implies, data is written to it, usually at the factory, and it can't be easily changed or erased by the user or even by normal computer operation.
So it's permanent, non-volatile storage. What's its job?
Its crucial role is storing firmware. This is the very low-level software that the computer needs just to start up to initialize the hardware, perform self-tests, and then load the operating system from your main storage drive.
Like the BIOS.
Exactly. The classic example is the BIOS, the basic input-output system. Or its more modern, flexible successor, UEFI, Unified Extensible Firmware Interface. That essential boot code lives on a ROM chip, usually right on the motherboard.
The very first thing the computer reads when you press the power button.
Precisely. Without it, the system wouldn't know how to do anything.
Okay. Now, moving to the more familiar mass storage. Let's talk about the traditional hard disk drive, the HDD. How does that mechanical beast actually work?
Right. The HDD is an electromechanical device. It stores data magnetically. Inside the sealed case, you have one or more rigid platters coated with a magnetic material spinning at high speed, often thousands of RPM.
Like tiny records.
Sort of, yeah. And then there's a mechanical actuator arm with a very tiny read-write head at the tip, almost like a record player's stylus, but it floats just above the surface. This arm has to physically move the head across the spinning platter to the correct track, and then wait for the right sector to rotate underneath it to read or write data.
Wow, lots of moving parts. Physics in action.
Definitely. And that's their defining characteristic. They offer huge storage capacities for a very low cost per gigabyte. That's their big advantage.
But the downside?
The moving parts. They make HDDs relatively slow. There's the seek time, the time it takes the ARM to move to the right track, and rotational latency waiting for the platter to spin to the right spot. These physical delays add up to milliseconds of access time. Plus, they're more susceptible to physical shock, make noise, and use more power.
Which leads us nicely to the modern alternative, the solid-state drive, or SSD. How does that work, and why is it generally preferred now, despite costing more?
The SSD is a complete paradigm shift. Its fully electronic solid-state means no moving parts at all.
Zero moving parts.
None. Instead, it uses a controller chip, which is like the drive's brain, managing a collection of NAND flash memory chips. Data is stored electronically within the cells of these flash chips.
And the advantages?
Dramatic speed increase is the big one. Because there's no physical movement required, access times are measured in microseconds, not milliseconds, often near instantaneous from a user perspective.
So everything feels faster. Booting up, loading apps.
Everything. OS boot times drop from minutes to seconds. Applications launch much faster. Files open instantly. It's probably the single biggest upgrade you can make to improve the overall responsiveness of an older computer.
Plus other benefits?
Yeah, because there are no moving parts, they're much more durable, resistant to shock and vibration, they run completely silently, and they consume less power, which is great for laptops.
The main trade-off historically was cost, right?
It was, yes. SSDs used to be significantly more expensive per gigabyte than HDDs, but that price gap has been narrowing continuously. They're still generally more expensive, but much more affordable and common now, even standard in many new systems.
Okay, so we have these super fast SSDs now, but you mentioned earlier the connection matters too. Let's talk interfaces. What's the deal with SATA and why did it become a bottleneck?
Right, so SATA, serial ATA, was the standard interface for connecting storage drives, both HDDs and early SSDs, for many, many years. It uses a specific cable and connector and a communication protocol that was originally designed with spinning hard drives in mind.
Designed for mechanical speeds, essentially.
Basically, yes.
Yeah.
It evolved over time, SATA 2, SATA 3. But the latest version, SATA 3, has a theoretical maximum throughput of about 600 megabytes per second.
Which sounds fast.
It is, and it's plenty for any hard drive. But even early SSDs could saturate that connection. As NAND flash technology got faster and faster, the SATA interface itself became the limiting factor. You had an SSD capable of much higher speeds, but it was stuck on this relatively slow SATA bus.
Like our Formula One car stuck in city traffic again.
Exactly that analogy. The drive had potential it couldn't use because the road wasn't fast enough.
So what was the solution? What broke that bottleneck?
The game changer was NVMe, non-volatile memory express.
NVMe. Sounds important.
It really is. It's a protocol, a language, designed specifically for accessing solid-state storage, for flash memory, from the ground up.
How does it achieve that speed? What's the architectural advantage?
The key difference is how it connects. Instead of going through the older, slower SATA controller architecture, NVMe allows the SSD to talk directly to the CPU over the PCI Express bus.
PCIe, the same high-speed connection used by graphics cards.
Exactly. PCIe is like a multi-lane highway directly connected to the CPU, designed for massive bandwidth and low latency. By using PCIe, NVMe bypasses the SATA bottleneck completely.
So the F1 car gets its racetrack.
Precisely. It unlocks the true potential of modern NAND flash. We're talking speeds for current high-end NVMe Gen 4 and Gen 5 drives of over 7,000 megabytes per second, even up to 12,000 megabytes or more.
Wow, that's more than 10 times faster than SATA 3.
Easily. And you feel that difference in demanding tasks. Loading huge game levels, 4K or 8K video editing, working with massive datasets, it removes that storage bottleneck.
Incredible difference. Okay, one last major piece of this puzzle, virtual memory. You called it a clever OS trick. What is virtual memory?
These are quite clever. Virtual memory is fundamentally a memory management technique used by the operating system. Its core idea is to create an illusion for each running program. The OS makes each program think it has its own private, large, contiguous block of memory addresses to work with its own virtual address space.
An illusion of more space than physically exists?
Often, yes. This virtual address space can be much larger than the actual physical RAM installed in the computer. It decouples the logical addresses a program uses from the physical addresses in RAM.
Why is that useful, apart from just seeming bigger?
Several reasons. It allows more programs to run concurrently than could fit entirely into physical RAM. It provides memory protection. One program can't easily access the memory space of another program or the OS itself, which is crucial for stability and security. And it simplifies programming, as developers don't need to worry quite as much about managing limited physical memory directly.
So how does the OS actually implement this illusion, this mapping between virtual and physical memory? You mentioned paging.
Paging is the most common method. The OS divides both the virtual address space and the physical RAM into fixed-size blocks called pages, typically 4 kilobytes, though sizes can vary.
Okay, uniform blocks.
Right. And the OS maintains page tables that map the virtual pages used by a program to their corresponding physical page frames in RAM. But here's the trick. Not all of a program's virtual pages need to be in physical RAM at the same time.
Where do the others go?
The OS uses a designated portion of the much slower persistent storage drive, your SSD or HDD, as a backing store. This is often called the page file, or swap space.
So it swaps pages out to disk.
Exactly. When physical RAM gets full, the OS's memory manager identifies pages in RAM that haven't been accessed recently, using algorithms like least recently used, or LRU. It copies these inactive pages out of RAM and writes them to the page file on the disk.
Freeing up that physical RAM frame for another page that is needed right now.
Precisely. It makes space in the faster RAM for the currently active working set of data and code.
That sounds incredibly useful, but also potentially slow. What happens when the program needs one of those pages that got kicked out to the disk?
That's the catch. When a program tries to access a virtual address whose corresponding page is not currently in physical RAM because it was swapped out, the hardware triggers a special type of interrupt called a page fault.
A fault sounds bad.
Well, it's not an error in the traditional sense, but it does cause a performance hiccup. When a page fault occurs, the OS has to step in. It pauses the running program.
Okay.
Then it has to locate the required page in the page file on the slow storage drive. It needs to find an empty physical page frame in RAM, or perhaps swap out another inactive page to make room. Then it copies the required page from the disk back into RAM, updates the page table, and finally it can resume the program that was waiting.
That sounds like a lot of overhead. Disk access is way slower than RAM access, right?
Orders of magnitude slower, thousands, even hundreds of thousands of times slower. So, while handling a page fault is necessary to maintain the virtual memory illusion, it's a significant performance penalty each time it happens.
And what happens if the system is constantly doing this, if it doesn't have enough RAM for everything it's trying to run?
That leads to a condition called thrashing. This happens when the system spends almost all its time just swapping pages back and forth between RAM and the disk, because the total memory demand of the active programs far exceeds the available physical RAM.
So it's constantly page faulting.
Constantly. The disk drive light is always on, the system becomes incredibly sluggish and unresponsive, and very little useful work actually gets done by the applications. It's just busy shuffling memory pages.
That sounds painful. And the solution is obvious, I guess.
Usually, yes. Thrashing is a clear sign that the system needs more physical RAM. Adding more RAM is often the most effective way to alleviate thrashing and dramatically improve overall system performance, especially if you multitask heavily or run memory-intensive applications.
It really puts the whole hierarchy into perspective. Okay, we've covered a lot of ground, from registers to virtual memory. To wrap things up, can you summarize how all these layers and technologies, SRAM, DRAM, SSDs, NVMe, virtual memory, all work together? How does this intricate system create the responsive experience we expect?
Absolutely. I think the key takeaway is that the smooth, responsive feel of a modern computer isn't just about raw CPU clock speed. It's fundamentally about this constant, intricate dance of data flowing efficiently through the memory hierarchy.
A well-choreographed dance.
You could say that. This tiered pyramid we've discussed, starting with those tiny instantaneous CPU registers, moving to the fast nearby cache built from SRAM, then the larger main memory workspace of DRAM, and finally the vast permanent library of persistent storage like SSDs or HDDs. It's really a masterclass in engineering trade-offs.
Balancing speed, size, and cost at every level.
Exactly. And the fundamental split between volatile memory, SRAM, DRAM, for the active computations, the stuff that needs power, and non-volatile storage, SSDs, HDDs, ROM, for keeping our OS, apps, and files safe when the power is off. That division really defines the system's architecture.
And the interfaces matter hugely, too.
Critically, the evolution from the limitations of SATA to the high-speed direct connection of NVMe over PCIe has been absolutely essential to let modern flash storage truly shine and keep pace with CPUs.
Removing those bottlenecks.
And then Layered over all of this, you have the clever operating system managing the illusion of virtual memory through paging. It lets us juggle more tasks than would physically fit in RAM, using slower storage as an overflow, albeit with that performance cost of page faults if we push it too hard.
So it's the synergy of all these parts.
It truly is. Understanding this hierarchy isn't just academic. It helps you diagnose performance issues like realizing you're thrashing and need more RAM, or understanding why an NVMe SSD makes such a difference. But more than that, I think it gives you a real appreciation for the incredibly complex, dynamic system that's constantly working behind the scenes to bring our digital world to life.
That's a great way to put it. And maybe a final thought for our listeners to ponder. How might future innovations change this picture? Could the lines between these memory types blur even further?
That's a fascinating question. We're already seeing technologies like Intel's Optane, though its future is uncertain, that tried to bridge the gap between DRAM and NAND flash. Perhaps we'll see even more integrated, tiered memory directly managed by the hardware or AI, making this hierarchy even more seamless and intelligent. It's definitely an area to watch.
Food for thought, indeed. This understanding really is crucial, whether you're a gamer chasing frame rates, a developer optimizing code, or just someone curious about how your computer works. Definitely make sure you tune in for our next deep dive where we'll explore the motherboard, the system's nervous system.
And thank you all for joining us on this exploration of the memory hierarchy. Please do subscribe to Tech AI and Beyond so you don't miss our future deep dives into the world of technology.